Oh, hello, this is Winston. We are just solving a Carnot cycle problem here. So the problem that we are solving is problem number 5.3 on page 145 of the Thermodynamics book. So the question reads, in a Carnot cycle operating between 307 and 17 degrees Celsius, the maximum and minimum pressures are 62.4 bar and 1.04 bar. Calculate the cycle efficiency and the work ratio. So assume air to be the working fluid. So first of all, it's a good practice to establish what is given to us here. So just to establish what is given to us here, we're given that the higher temperature number one being 307 degrees Celsius, and temperature 2 being 17 degrees Celsius. Alright, and we have our operating pressures here in the highest pressure, so P high is equal to, so your high pressure is equal to 62.4 bar, and the low pressure is equal to 1.04 bar. So first, what is asked from us here? So what is asked from us here is to do the first is the cycle efficiency, so that will be the thermal efficiency of the Carnot cycle. So thermal efficiency of the Carnot cycle, is equal to 1 minus the temperature, the low temperature in Kelvin, so that would be 17 plus 273.13 all over 307, the higher temperature, which is 307 plus 273.15. So it's important that the temperatures be converted to Kelvin, otherwise you will have the wrong ratios. And what we get from that is a result of 0.050129. That is our thermal efficiency, or thermal efficiency of around 50%, 50.0%. Okay, so that is our Carnot thermal efficiency. That's 50%. Now on to the second part of the question. The second part of the question asks us to find the work ratio. Now the work ratio is equal to the it's equal to delta T delta S all over the this is the gross work that the system applies. So gross work. So delta T, we already have that. Now we have to find delta S. Now in order for I to find delta S, we need to make use of the TS diagram that we have here, since we don't know what delta S is exactly. So for the high temperature here, they gave us high temperature of 62.4, and we have low temperature of 1.04. Now we need to know this basically here. We need to know delta S. But in order to find that, we need to do two processes. So first, we'll have a point here, point A. That's where the lower pressure interacts with the higher temperature that we have here. So the higher temperature again is 307 degrees Celsius. Lower temperature here is 17 degrees Celsius. So we need to find this point A there where the lower pressure intersects with the higher pressure. Or sorry, with the higher temperature that we have here. We need to find the difference from this point 1 here to point 2 to find delta S. Now there's 4 points there, so what we need to find is, the two steps that we had is we need to find the difference from point 1 to point A here, and from point A to point 3 there. That's a isobaric process, so we need to find that the difference here. Once we have measured that, we can find delta S. So starting off here, we need to find the distance from point A to point 1 there. So point A to point 1, we have S at A minus S at 1 is equal to, that here is a constant temperature line, so it's an isothermic operation. So for an isothermic operation, we will have R ln of the high temperature over the low temperature, or the high temperature over the low pressure rather. That'll be plug that into a calculator, and you get 1.17508. Now, for the second part of the equation here for finding delta S, so to find the second portion here, we need to get from this point here to this point. That's an isobaric operation. So for that isobaric operation, we go from SA to, that's SA to S3. So for for that operation from SA to S3, that is an isobaric operation, so that is equal to Cp ln of the high temperature over the low temperature. Again, the temperatures need to be converted to Kelvin for this to work, otherwise you'll have the wrong ratios. So 17 plus 273.15. Okay, so I plug that into the calculator, you get 0.696353 as a result there. Now, to get delta S here, so since this one here is from S1 to SA, and this is from S3 to SA here, we need to subtract them. So just subtract them to find delta S. So delta S is equal to 1.17508 minus 0.696353. If you plug that into a calculator, you get the value of delta S as 0.478727. Alright, now we have found delta S. Now the only thing we need to find our work ratio is the gross work. Now to find gross work, we need to do two steps as well. So to find gross work is equal to the work from 1 to 2 plus the work from 2 to 3. So that is our gross work there. So we'll just write that down here. Work from 1 to 2 plus minus work from 2 to 3. So why I'm writing minus here is that because gross work is equal to net work, and net work is equal to minus work that's applied. Okay, so to get minus from work 1 to 2, that is equal to S2 minus S1, that's the number that we got earlier, times the higher temperature, T1. So that is equal to 0.478727 times the higher temperature. Again, temperature should be in Kelvin, so 304 plus 273.15. So that'll be equal to 277.733. So that's work from 1 to 2. Now work from 2 to 3 is a little bit different because it is an isentropic operation. So we will be using a different formula for that. So that's minus work from 2 to 3. That'll be equal to CV T1 minus T2. So to get that value, CV for air is 0.718, and T1 again, just temperatures in Kelvin here. So let's just write that down. Temperatures in Kelvin, 17 plus 2 and 3.15. And okay, so that is our equation there. Once we have our equation, plug that into a calculator, you get a value of 208.22. Now, to finally find our work ratio here. So work ratio. Okay, work ratio is equal to, again, T1 minus T2. So T1 minus T2 here is 273.15 minus 17 plus 273.15 and times delta S. So delta S that we got earlier, just a reminder, is 0.0478727. all over the gross work. So gross work is the work that we had from 1 to 2 added to work from 2 to 3. So those are numbers that we got. So that's 277.733 plus 208.22. So that gives us a final result of a work ratio of 0.286 as our work ratio. Right? So thank you very much.